I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again, Lord. I thank you for the students, and I just pray that you'd guide our thoughts today. Help me to think clearly and to communicate effectively, Lord. In your name I pray. Amen. All right. So we were, again, what are we trying to do? Our goal is to solve dx dt equals to ax, where A is a n by n real matrix, right? So this is a nice notation for system of n linear homogeneous ODEs with constant coefficients. Right, so we've been working on solving this problem for a few classes now, and we know that if we can find eigenvectors for the matrix, then that gives us a bunch of solutions, right? And sometimes the eigenvalues are complex, then we need complex eigenvectors. Those give us other kinds of solutions. But even with all of that said, we've learned that that's not enough to form fundamental solution sets, right? There are examples where eigenvectors and complex eigenvectors are not enough. So what we figured out at the end of last class is that we can look at the matrix exponential, right? Matrix exponential, and that was e to the ta, which is equal to I plus ta plus 1/2 t squared a squared plus dot 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 dot. I mean, if you want a nice formula for it, this is the sum n equals 0 to infinity of, let's say, t to the n, a to the n over n factorial. And so last time I worked out that, what did we work? We worked out a couple things towards the end of last class. We worked out that, number one, that e to the ta inverse is just equal to e to the minus ta, right? Which means that e to the ta is invertible, right? Which another way of looking at is that the determinant of e to the ta is not equal to 0. All right? What's that mean? Well, that means that if we look at the columns of the matrix exponential, they're linearly independent functions. All right? So this then implies the columns of e to the ta are linearly independent vector valued functions of time, which means that they might be solutions, right? They're the right kind of thing to be solutions to the differential equation we're looking at. And then the other thing we showed was we showed that this has d dt of e to the ta. We got that that's equal to a e to the ta. So this means that e to the ta is a so-called solution matrix. Let me just talk a little bit more about solution matrices before we go on here, because I got a little bit shortchanged last time. Let's talk about solution matrices. I want to expand a little bit the discussion last time. So if x, x1, x2, xn is a matrix of functions of t, then we can calculate the derivative of that matrix with respect to time. And the definition of the derivative of a matrix is just that we differentiate each component separately. So what that means is that you could also look at it as differentiating each column separately. So this is actually what that means. So the derivative of a matrix of functions is the matrix of derivatives. And when you have dx dt equals to ax, we say x is a solution matrix for dx dt equals to ax. Solution matrices are neat for the following reason. Yep.
Question. This is probably the question here, but I'm looking at your notation for the top matrix, and you have those lines in between
Yeah.
spectrum on x equals 2.
Mm-hmm.
How would that be represented in matrix form, I guess?
Sure. We could have
I guess I'm just not sure.
t squared, t cubed, t to the fourth. So I'm thinking that would be like x1, x2, right? So like x1 here would be t cubed, and x2 would be t squared t to the fourth, just to give you an example of what I mean by that notation.
Okay, so you're just pulling the two matrices together.
Right. We can look at a square matrix as a bunch of columns glued together. And the reason to do that is the following linear algebra fact. So here's a fun fact from linear. Well, that's probably wrong. Matrix theory is probably more accurate. That may even be too strong, but here it is. If I take a times x, all right, which is a times x1, x2, xn, all right, it is a fact of matrix multiplication that you can look at that as column by column multiplication of a. This is ax1, ax2, axn. So this is just basic matrix multiplication fact. So if you look at that, right, which I'll sometimes call this the concatenation proposition. Some people call it column by column multiplication. So the column by column multiplication of A, right, on X. So put that together with this right here. What do you got? So if you look at this paired with that and that, what do we have all together? Let me put it all together. We have dx dt equals to ax is true if and only if what? If only if, like, dx1 dt, dx2 dt, dxn dt is equal to ax1, ax2, axn. Right? So if we have a solution matrix, we have this equation which says what? I mean, if you look at star, what does star yield? If a matrix equation is true, it has to be true column by column, right? So if we look at the first column of this matrix equation, what does it tell us? We get that dx1 dt equals to what? ax1. If we look at column 2, what do we get? Yeah, dx2 dt equals to ax2. And so forth. The nth column gives me dxn dt equals to axn. So this, application of this discussion is that if I look at x equals to e to the ta, right? And if I think about that being x1, x2, xn, then each column is what? Is a solution to dx dt equals to ax. So this is great, because we can calculate this matrix exponential for any matrix, and apparently it's got n linearly independent solutions in it. And that's all we need for the general solution, so I guess we're done, right? Except what's the devil's in the details, right? The question is, how do you actually calculate the columns of the matrix exponential, all right? Now, we got away with doing it directly for an example last time, but that was kind of special, right? Sometimes you can do it directly. Let me show you an example, a direct example. If I have a equals to, let's say, 3, 1, 0, 0, 3, 1, 0, 0, 3, all right, then you can calculate that a minus 3i is what? It's this, right? So what's a minus 3i squared? When you square that matrix, it just moves the 1 up to the upper top diagonal, right? Because this times that gives me that 1, but all the other products are 0. How about a minus 3i cubed? Well, that's 0, right? So for this very special matrix, we can calculate the matrix exponential directly. Well, that's still a little bit of a lie. Let me show you, though. So you kind of have to make it appear. I have e to the ta, right? I know that a minus 3i is special for this matrix, right? Something nice happens for it. How do I make that a minus 3i appear there? How about we just add 0, right? So like I can say this is a minus 3i, which I like. I got lots of warm fuzzy feelings about a minus 3i as it relates to this matrix, and then I add 3i. There I just added 0. But then by properties of the matrix exponential, this is e to the 3it times e to the t times a minus 3i. Because going from here to here, I'm allowed to do this because 3i commutes with, well, 3it commutes with t times a minus 3i. In fact, any multiple of the identity matrix will commute with another matrix. Now, e to the 3it, what's that? What does that mean? E to the 3, that's e to the 3t, 3t, 3t. You can work out through direct calculation that that's actually e to the 3t, e to the 3t, e to the 3t. Zeros elsewhere. So that front factor just works out to e to the 3t times the identity matrix. So that's the front term. And then the second one, by the definition of the matrix exponential, is what? That's I plus t times a minus 3I plus 1/2 t squared a minus 3I squared. And do I need any more? I don't really need any more. Everything beyond that's 0, right? A minus 3I cubed is 0. If a minus 3I cubed is 0, a minus 3I to the 4th and the 5th and the 6th, whatever else, the series truncates. Those are all the non-trivial terms in the series already. I don't really need the plus dot dot dot. And so I can be explicit. This is actually e to the 3t times what? 1, 0, 0, 0, 1, 0, 0, 0, 1 plus t times a minus 3I, which is what? 0, 1, 0, 0, 0, 1, 0, 0, 0 plus t squared over 2, 0, 0, 1, 0, 0, 0, 0, 0, 0, lots of zeros. That's the matrix exponential. By straight calculation for this problem. Okay, it wasn't entirely straight, was it? It was a little bit crooked, wasn't it? I had to create this a minus 3I factor in order to use it, didn't I? So the ones that you could sort of calculate most directly and sort of the most straight path would be if you had a matrix like a to the 3rd power was 0. Then you could just straight calculate it, right? But anyway, so let me conclude here. So we have e to the t, e to the ta. We just worked it out. It's what? It's, if you multiply the e to the 3t through, we get what? E to the 3t, right? And then zeros, first column. What's my second column? I get a t e to the 3t. Anything else? That's it for, well, yeah, yeah, you're right. The middle one is what? E to the 3t. 0, right? And then anything, third column. Looks like I pick up a 1/2 t squared e to the 3t, right? And what else do I got? T e to the 3t. And e to the 3t. So that's a fundamental solution matrix, right? I can write down the general solution. So what's the general solution? X equals to C1. I'm going to start, I'll pull the e to the 3t out because it's easier. E to the 3t, 1, 0, 0. Plus C2 e to the 3t t 1, 0 plus C3 e to the 3t t squared over 2 t and 1. There you go. That's the general solution built from the matrix exponential in a somewhat sneaky way. Let me explain to you where this example comes from. So this matrix A, what's the characteristic polynomial of this matrix? A little bit off. Thanks. So what's the characteristic polynomial of this thing? Its determinant of a minus lambda I is what? Looks like 3 minus lambda what? You just plug it in. It's 3 minus lambda cubed equals to 0. All right? So, of course, you could also look at this as lambda minus 3 quantity cubed equals to 0. That's the characteristic equation. There's something called the Cayley-Hamilton theorem. What the Cayley-Hamilton theorem says is that a matrix will solve its characteristic equation. So Cayley-Hamilton theorem says it says the following. It says that if I plug in lambda equals to A, and I change the 3 to the corresponding matrix 3, which is 3i, that cubed has to be equals to 0. This is what the Cayley-Hamilton theorem says. It says a matrix in the correct interpretation solves its characteristic equation. So if I've got a matrix that's so nice like this to just have such a simple characteristic equation, then I knew as soon as I wrote this down that this would have this property, that a minus 3i cubed would be 0. And I know if that's 0, then I can work out the matrix exponential through this algebra. But the thing is there's matrices which don't just have one eigenvalue, right? We got ones that have got like an eigenvalue 1 and an eigenvalue 2 twice. We got ones with real and complex I mean, there's a lot of other things that happen, right? So this method of calculation isn't going to be a general method, is it? Like I said, this is really special to this really nice matrix. So what do we do? So this is kind of embarrassing. We've got this solution matrix. It's beautiful. It's got all the solutions we could ever dream for, and yet we got no way to really get our paws on them at the moment. And that's where the following result and definition comes into play. A has generalized eigenvector order P with eigenvalue lambda if A minus lambda I to the P, I should probably give the eigenvector a name, let's call it V. If that times V is equal to 0, yet A minus lambda I to the P minus 1 on V is not equal to 0. So this is a generalized eigenvector order P. So for example, if we put P equals to 1, what does it give us? So P equals to 1 is an ordinary eigenvector, right? Yes?
I think we're like 7 weeks in, but what is ODE?
Nah! This is an ordinary. That's a hilarious question at this point. Ordinary differential equation, yeah. And then, of course, the question is, what on earth does that mean, right? Yeah. So the ordinary means that just derivatives with respect to the single independent variable. To give you a contrast, if you look at something like the divergence of the magnetic field equals to 0, what that is partial B1 partial x plus partial B2 partial y plus partial B3 partial z equals to 0. And if we're not in the magnetostatic context, the magnetic fields are functions of time and space. So you have, in fact, 4 independent variables. And the Maxwell's equations involve all 4 partial derivatives with respect to all 4 of these. That's why Maxwell's equations, this is one of them, the no magnetic monopoles equations are examples of partial differential equations, which we'll talk about towards the end of this course a little bit. Not Maxwell's equations. That would be crazy. But how to solve some basic PDEs like the wave equation, the heat equation, like waves on a string, stuff like that we can do. Other questions about that? That was restful because this is much harder. Thank you. So an generalized eigenvector, order v, is something like this. Now, there's more than this. We like to have them in chains. So chains, what I'm talking about is we have something like this. A minus lambda I v1 equals to 0. A minus lambda I v2 equals to v1. A minus lambda I v3 equals to v2. All right, you get the idea. Dot, 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 dot. A minus lambda I v, let's say, k equals to vk minus 1. This altogether makes v1, v2, dot, 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 vk a so-called k-chain of eigenvalue lambda. You say, well, that's lovely, why do you care? Well, if you have v1 through vk which satisfy this chain condition, it makes them linearly independent, provided they're non-zero. All right, it forces linear independence on the chain. And more to the point here, I'm supposing that these are all non-zero, okay? So what can we say about v2 if it satisfies this condition? Well, how about a minus lambda I squared on v2? What's that equal to? Multiplying by a minus lambda I here gives me that a minus lambda I squared v2 is a minus lambda I times v1, which is by assumption 0, right? Aha! So therefore, v2 is generalized eigenvector ordered what? 2 for lambda. What happens if we do the same trick on v3? What if we take v3 and multiply by a minus lambda I both sides? What do we get? Well, we just figured out that a minus lambda I v2 is what? Well, by definition, what is this? That's v1, right? I'm sorry? Oh, okay. So I'm taking the third one, multiplying by a minus lambda I. So I get a square here, and I get, now that we're still not done, what happens if we multiply one more time by a minus lambda I? Yeah. So now I have a minus lambda I cubed on v3 is equal to 0, right? And so therefore, v3 is generalized eigenvector order 3 for lambda, right? For eigenvalue lambda. And you can see it's order 3, right? Because if you look at the square on v3, it's v1, which is by assumption non-zero. So this imposes the p minus 1 not being 0 on each level, this chain condition. And you see where this is going. This will, of course, give us that a minus lambda I to the k on vk is equal to 0. And yet, if I look at the k minus 1 power, it's going to be non-zero. Right? Okay. Now, before I show you how this solves differential equations, let me just give you an example of this. We can pick on this matrix. This one right here, we can find a 3 chain. Oh, that's unfortunate. Tell you what, I'm going to change it up so it's not 2, 3, too many 3s. Let's put 2s here. There we go. So if you look at a minus 2I, what do we get? Right? So let's try it out. What's a minus 2I times E1. I'll write out E1. E1 is what? 1, 0, 0. What happens when I multiply this times that? What do I get? So E1, or 1, 0, 0, is what? It's an eigenvector with eigenvalue 2 for this matrix. What happens when I do A minus 2I times 0, 1, 0? Yeah, I get 1, 0, 0. Right. And how about when I look at A minus 2I times 0, 0, 1? What's that give me? 0, 1, 0, right. So it's easier to write this in the following notation. A minus 2I E1 equals to 0. A minus 2I E2 equals to E1. A minus 2I E3 equals to E2. So if we put that all together, what we have is that E1, E2, E3 is a 3-chain for lambda equals to 2. One of the major achievements of linear algebra is to prove that for any matrix, you can construct a basis for that matrix made of chains of generalized eigenvectors. So this is like a general construction. You can't, so supposing all the eigenvalues are real, you can always find a basis for Rn, which is constructed, which is just built from these chains of generalized eigenvectors. There's always enough vectors to go around to find these chains. And if your eigenvalues are complex, well, then you can look at chains of complex eigenvectors. And if it's a real matrix, they come in some sort of conjugate pairing. But so that's great. You're like, yay, linear algebra, woohoo. But what does this have to do with our problem, right? Let's look at that. What happens when you take the matrix exponential and you feed it a chain of generalized eigenvectors? What happens then? So let's talk about the interaction of e to the ta and generalized eigenvectors. I guess first thing we should talk about is what happens when you have, let's suppose you have, easiest case is what? How about this? When we have a v equals to lambda v, what happens? What happens when we hit the matrix exponential by an eigenvector? I take e to the ta, right, times v. What's that equal to? First of all, schematically speaking, what this is a linear combination of columns of the matrix exponential. What is a matrix times a column vector? This is a linear combination of the columns of the matrix, right? If every column of the matrix is a solution to the differential equation, it follows, since the differential equation is homogeneous, that the sum of solutions is again a solution, right? So this is a solution to dx dt equals to ax, supposing that v is an eigenvector. Actually, even if v is not an eigenvector, this is still a solution, provided, it doesn't matter, actually. This v, if it's a constant vector, this is a linear combination of the columns of the matrix exponential. That's a solution. But let's see why it's an interesting solution if it's an eigenvector. What happens to this? I'll write it out in the expanded notation because that's easiest for you guys to follow. What happens when v multiplies here? we get v, IV, right? Plus TAV plus 1/2 T squared A squared V. So that gives me what? Lambda V, right? What happens when we multiply 2 times on V? What happens there? We produce 1 lambda from the first application of A and another lambda from the second application of A, right? So this gives me T squared lambda squared V. There's a V everywhere. You can pull it out. What is that? Well, you better learn. We're about to start doing series solutions to differential equations. It won't be long. I can feel it coming. It's on the horizon. It's around the bend. This is something you need to pick up the pace on. That is the power series of the exponential of T lambda. This is, in other words, this is e to the T lambda. Wait a second. This is what? This is our eigensolution, right, from 2 lectures ago and last lecture. This is the eigensolution. So matrix exponential times eigenvector reproduces our beloved eigensolution, which covers about 80% of what you face in applications, especially if you allow the complex case. I'll do it over here. Magic formula. Here we go. E to the TA equals to e to the T. And what I'm going to do is I'm just going to replicate the thing I did in example 2. I'm going to add and subtract lambda I. Right, this is what I did in example 2. Remember, I subtracted and added 3i because that was my lambda. So just basically repeat that trick. And this is going to give me e to the T lambda I times e to the T times a minus lambda I. Going from here to here, again, that's because lambda IT commutes with T times a minus lambda I. So I have the laws of the matrix exponential laws of exponents work for commuting matrices. And this e to the T, I'll work it out fine. E to the T lambda I is what? This is the sum, n equals 0 to infinity, of T to the n, lambda to the n, I to the n, over n factorial. But what is I to the n? This is just I, so I can pull it out. And I've got a sum, n equals 0 to infinity, of T lambda to the n over n factorial, otherwise known as I e to the lambda t. There you go. There's the proof. What I did with the 3t works just as well for lambda. So this simplifies. That's just e to the lambda t times the identity matrix. All right? And I don't, in some sense, don't even really need to write that. And this right here, well, we can expand. This is I plus t times a minus lambda I plus t squared over 2 a minus lambda I squared plus t cubed over 3 factorial. It goes on and on, all right? That right here, guys, is what I refer to as the magic formula because it's where the magic happens. So if you look at the magic formula, right? What happens when you hit it with like a generalized eigenvector? What happens when you hit the magic formula with a generalized eigenvector of order lambda? So suppose that a minus lambda I squared v2 equals to 0, and a minus lambda I v2 is actually equal to v1. Sorry, I have stated this inefficiently. So a minus lambda I. So I'm trying to say v1 and v2 are a chain of generalized eigenvectors, okay? What happens when we calculate e to the ta times v2? What happens there? So we have e to the lambda t, right, times v2 plus t times a minus lambda I times v2 plus 0. See, because everything higher vanishes. So what does that leave you with? This leaves us with e to the lambda t times v2 plus t times v1. This is how the t's appear in the solutions. They appear because of the matrix exponential and these generalized eigenvectors. They create possible t's or t squareds in the solutions. Like we already saw in example 2, we have a t squared times an exponential. So to summarize the solution technique, you find your chains of generalized eigenvectors, and then if you multiply those by the matrix exponential and use the magic formula, you actually are able to calculate specific formulas from these chains, because the series truncates, as we just saw. Let me work an example. We can get rid of this, I think. Any questions before I foolishly erase something? Okay. What example am I on here? Let's see here, I can't count. Example 4, I guess, right? Yeah. Let's see here. So I'll work a 3x3 example. Actually, let's kind of work out the let's work out that one with the 2's, since we already got our chain for that one, right? So we found that a minus 2I E1 equals to 0, a minus 2I E2 is equal to E1, and a minus 2I E3 is E2, right? Okay, so let's construct solutions by magic. By the magic formula, what lambda are we going to pick? This magic formula holds for arbitrary lambda. It could be complex as well, but only in the case that lambda is actually an honest-to-goodness eigenvalue for your matrix do there exist vectors which truncate the series. This is just an algebra identity, but it's most useful for eigenvalues for this matrix. This matrix, we want to put lambda equals to 2, you know? So, so we take e to the ta times e1, right? And that's going to work out to e to the 2t times e1, right? Or if you like, that's e to the 2t times 1, 0, 0. So there's one of my solutions to this problem. Say that's x1. x2, I should take e to the ta times e2. Now, more specifically, that is e to the 2t I, right, plus t times a minus 2I, right, plus dot, 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 dot. That multiplies by e2. What happens, though, when we multiply this by e2? That simplifies, right? So we get e to the 2t. I times e2 just gives me e2. What happens when I hit e to the 2, e sub 2 on this? We get e1, right? So I get plus t e1. Explicitly, that's e to the 2t times t, and I've got a 1 here, and I got a 0 here. There's my second solution via the matrix exponential. My third solution via the matrix exponential for this problem, e to the ta times e3, because that's the third thing in my chain. Use the magic formula, e to the 2t I plus t times a minus 2I plus t squared over 2 a minus 2I squared plus stuff that doesn't matter, e3. So what's that give me? That gives me e to the 2t. The I gives me e3. And then I get plus t times what? T times e2. And then I get plus t squared over 2 times what? Let me explain this last piece. So when this hits that, what happens? The first copy, when it hits E3, what happens? It goes to E2, right? Then the second copy of A minus 2I, when it multiplies E2, goes to E1. And that's why I have to write E1 here. So by the time you get to the end of it, the whole chain appears in the solution, right? At the level of the eigenvector, just the eigenvector appears. When you get to order 2, the eigenvector and the order 2 appears in the formula. When you get to the third one, the first, second, and third things in the chain appear. Now, of course, this is e to the 2t times explicitly t squared over 2 t and 1. You can recognize, yeah.
Sorry, you probably explained it with the green marker, but why isn't it E1 first? Like why is it E3 plus T E2 instead of...
See, because when I take a minus 2I times E3, that's E2. When I have the identity matrix times E3, it just gives me E3. So I'm doing nothing more than applying the chain conditions to the magic formula step by step. But if you look at these solutions we just found, x1 and x2 and x3, they should be familiar, right? These are exactly what we derived by the direct Cayley-Hamilton solution over here, right? Look at this. Here's my eigensolution. This is like x1, right? This is like the x2, is it not? This is like the x3. Now, of course, we've got 3 instead of 2, but you can see it's the same song and dance. Now, I have to be careful, you guys. I can't just ask you to do this calculation for arbitrary matrices, because generally finding the chains of generalized eigenvectors is a computationally intense problem. So I have to stay kind of close to these examples. Otherwise, the algebra of finding the generalized eigenvector becomes sort of onerous. But for 2x2 problems, we can always work. You can always work a 2x2 problem, and that's where I tend to test. And these calculations are even necessary in the 2x2 case. Let's see if we can go back and solve that problem we came up with by reduction of order. Yeah. Let's see here. So if we look at, let me reverse engineer the problem here. Always an important idea. for the future. So if we have y prime prime plus 2y prime plus y equals to 0, you know that y equals to e to the minus t, and y2 is t e to the minus t. Those are solutions which appear, right? Because we've got a repeated eigenvalue of lambda equals to 1. Minus 1. Yeah. So what's the corresponding matrix problem? If I put x1 equal to y, and if I put x2 equal to y prime, I'm really annoyed. I had problems worked out on a piece of paper that I was carrying with me last time. I don't know where those papers went. I had examples already made for us, but I could not find them despite my efforts before class. So anyway, I have to make an example up for us right now, so bear with me. So x1 prime is x2, and x2 prime is what? It's minus 2y prime minus y, aka minus x1 minus 2x2. All right, great. So here's our problem. x1, x2 prime equal to 0, 1, minus 1, minus 2. I believe this problem will give us the necessary difficulty. Here's my a, right? What are the eigenvalues of a? Okay, good. So this has eigenvalue minus 1 repeated. All right? What are the eigenvectors? Eigenvector for lambda equals to minus 1. So what do we have to solve? We have to solve a plus I u1 equals to 0, which is what? 1, 1, minus 1, minus 1, uv equals to 0, 0. Don't think we need row reduction for this one, right? Pretty clear that our equation is u plus v equals to 0, right? So we can put u1 equal to, say, 1 minus 1. This is a decent choice, right? Now I told you that linear algebra says that a chain of generalized eigenvectors exists and you can find it. It's just a matter of looking for it. So if I want to find a chain, right, because I know that if I hit the magic formula with chains, it's easiest calculationally. What do I need to look for? I need to search for u2 such that what? A plus I times u2, right, equals to u1. So one of the neat things about the calculation here is we never actually have to square a plus I. I mean, I'm looking for a generalized eigenvector of order 2, but you notice if you look at those chain conditions, which I have annoyingly erased at this point, there are no squares or cubes or anything in there. They're all just a minus lambda I times vector equals vector. So we actually, in the calculation here, never actually have to square the matrix, in contrast to example 2. But okay, so this is same matrix we just had, 1, 1, minus 1, minus 1. The u and the v we don't know yet. u1, see, you got to make a choice. Once you make that choice, you got to stick with it. So u1 is 1 minus 1. So now we got two equations and two unknowns, but they're the same equation, right? So we got u plus v equals to 1. Now usually we can't set a variable equal to 0, can we? Most of the time we've been looking at the problems, and like it's been typically a bad move to put the variable to 0. You guys keep trying to do it to me, but we can't do it. But the tables are turned here. We can make v equals to 0, and it's okay, right? So easiest solution is just to set v equals to 0, which makes u equals to 1. So my u2 will just be 1, 0. So the only kinds of matrices I'm going to ask you to find chains of generalized eigenvectors for explicitly is like an ugly 2 by 2 problem. I can make the 2 by 2 problem as ugly as I want to. You can still hack the algebra because it's just this. All right? 3 by 3, I'm kind of going to have to give you a matrix that's basically in the shape of example 2 if I'm asking you to explicitly find eigenvectors, so, and chains of generalized eigenvectors. So like, long story short, for those kind of 3 by 3 or 4 by 4 problems, what's called the standard basis is going to be your, the standard basis is this, E1, E2, E3 is the so-called standard basis. That'll end up being the chain that you're looking for. I'm unwilling to ask you guys more complicated 3 by 3 questions, except, maybe in the homework, probably not even there. Although, admittedly, if I actually had my sheet with me and I could find that example we did, we could actually find the third solution for that one. We found 2 solutions that needed 3. You could actually go back there and find a generalized eigenvector to find the third missing solution. Okay, so, but I'm trying not to clutter things with overly complicated examples today. So, let's put it together. So what's our solution then? So x1, we don't need to belabor that. That's an eigenvector, right? And so we do e to the minus t times 1 minus 1. This is still same song and dance as from before. We still have the eigensolution. We don't need the magic formula for that. You can derive it from that if you want, but there's no need. How about x2? The second solution is e to the ta times u2, which here, magic formula, e to the 2, listen to me, e to the minus t times I plus t times a plus I plus stuff times u2, right? But what's that work out to? By construction, that's u2 plus t times u1, right? And the higher order things vanish because this is a generalized eigenvector of order 2, which means that a plus I squared acting on u2 is 0, as is the cube and the fourth and everything else. So that's it. That's the non-trivial contribution of the matrix exponential when you multiply u2 on the right for it. And then, of course, this is, in detail, this is e to the minus t times what? What was u2? 1, 0 plus t times, what was my u1? 1 minus 1. So I get what? I get e to the minus t plus t, e to the minus t, and I get minus t e to the minus t down here. Therefore, general solution is what? We get x